Okay, so now let's see how to use OpenMP to write shared memory programs. Okay, so OpenMP is an open standard. Okay, so that means that it defines what OpenMP includes, features that it includes, but it doesn't specify an implementation. And so there are actually multiple implementations of OpenMP by different vendors. And you can use OpenMP with either C or C++ or Fortran. So OpenMP is based on these things called compiler directives. Okay, so they're basically, basically, let's say that you use OpenMP with C. So then you just write a normal C program, and then you add these little extra keywords or little annotations. Okay, and these annotations tell the program how to do the parallelism. Okay. So, so the nice thing about this process of just using these compiler directives is that if you write an OpenMP program with these directives and you give it to an OpenMP compatible compiler, right? Then of course that compiler is going to spit you out some parallel code, okay? That code that can run in parallel. But you can also take these OpenMP programs with the compiler directives, and if you give it to just a normal sequential compiler, right, that doesn't know anything about OpenMP, right, then that program can still compile. Okay, that program is still correct to the non-compatible compiler. Okay, so then oh right, and then there are several OpenMP compilers available. For example, one good one is the one from Intel. Okay, so so now because you can write these, you can just incrementally add these directives to a program, right? And then the program is always going to be correct both to OpenMP compilers and just normal sequential compilers. Okay, so because of this, then you can add parallelism to your program incrementally, right? So for example, if you have a big long program, maybe you don't have enough time right now to make everything parallel. Okay, so you can just take certain parts of it and make that parallel to start out with, right? Maybe you can take some of the big loops and make those parallel. Okay, and then later on, you can add more parallelism as you get more time. Okay, so that's a nice way to transition from, you know, if you have a sequential program right now, it's a nice way to transition it to a parallel program. Okay, so yeah, so as I mentioned earlier, OpenMP still uses threads underneath. Okay, however, the programmer doesn't need to manage the threads by himself. Right, the OpenMP system is going to do that. Okay, but because you don't actually have explicit control over the threads, then you can't quite do as many things as you can with things like Java or pthreads. Okay, but for most tasks, OpenMP is entirely capable of solving those. Okay, so OpenMP is based on threads, and it uses this fork join model that we talked about. Right. So so again, that's where you have a master thread at the beginning, right? And then when you have parallel work, so in OpenMP, these parallel sections are called parallel regions. Okay, and these regions are executed by a team of threads. Okay, and here the compiler is going to take care of creating these parallel regions. Okay, so it's going to create the threads at the beginning of the parallel region, and then at the end, it's going to destroy the threads. Okay, so the programmer doesn't need to worry about that. Okay, so if you want to, so we're going to go through some of the main features of OpenMP, but if you want to get more details, you can go to this website. Okay, so the first thing to talk about is how do we do these parallel regions, right? Because that's where the parallelism occurs. Okay, so in order to start a parallel region, right, we want to make sure that we have many parallel threads, right? Because initially you just have one master thread, and when you get to a parallel region, you need to create a bunch of a team of threads. So the way that you create a team of threads is using this compiler directive, this parallel compiler directive. Okay, so what you write is simply so you add this line to your program, you add this pragma OMP parallel. Okay, and then once you do that, then this creates a team of threads, and the team of threads will now execute the next block of code. Okay, so the block of code is enclosed in these curly braces, and whatever code is in here will be executed by the team of threads that's created. And then at the end of this block of code, so at the end of the parallel region, right, the threads are going to do a join. And then that means that you go back to having just a single master thread. Okay, so how many threads do you have? So this is not specified, okay? But when you actually run your program, then you have some ways of controlling this. So for example, you can use a number of threads clause after your parallel directive. Okay, so that's a suggestion to the runtime system how many threads you want. Okay, you can also call this function OMP set number of threads, right? And then if you want to check how many threads you currently have, you can, there's this environment variable OMP number of threads. Okay, and the recommendation is that you use one thread per processor or core. But sometimes you can use more if the threads are really lightweight and they're not doing too much. You can have multiple threads per core. Okay, so so once you start that team of threads, right, then they're all going to be executing this code in the following block. Okay, but of course you don't want all the threads to do the same thing in that piece of code, right? Because in that case you would be just repeatedly you would be doing redundant work, right? You don't want everybody to do exactly the same thing. So in order for the threads to do different things, you can have them do different things based on their thread ID. So this is just like in MPI, where all of the processes run the same program, right? But you can get them to do different things based on their process ID. Okay, so here it's the same concept. Now, another way that you can get threads to do different things in this parallel region is to use these work sharing constructs. Okay, so there are a few of these, and I'll go through these in more detail later. Yeah, and then these parallel regions can actually be nested. Okay, so we looked at how forks can how slave threads can fork off more slave threads, right? So that's an example of nesting, nested parallelism. Okay, so here's an example of using these parallel regions. So we have this. So if you add this stuff to your program, right, then here when you write the pragma OMP parallel, you're saying that I want several threads. Okay, so then the runtime system will create multiple threads over here. This statement over here about private. Okay, so we'll talk more about this later, but this is basically defining which variables are shared or not shared. Okay, so this private means that each thread will have a variable called IAM and then also MP, right? And then these variables are not shared between the threads. Okay, so the threads can share variables, right? Because we're in a shared memory setting. But in this case, we don't want the different threads to share these variables, so we declare them to be private. Okay, so then following this this pragma OMP parallel, right? Then you have your parallel region. Okay, and this parallel region, all the threads that you create will execute this parallel region here. So so what they're going to do is, first of all, they're going to count how many threads there are. Right, so this is kind of like that hello world example for MPI, right, where you look up how many processes are in your communicator. Okay, so here we have a function OMP get number of threads that tells you how many threads were started up. Okay, and then also the threads have thread IDs. Okay, so if you started let's say k threads, right, then the thread IDs are going to be numbers from 0 to k minus 1. So every thread will have a different thread ID. And this is how you make the threads do different things. Or this is one way you can have them do different things. Okay, and then next, so we're going to do a hello world again. So we're going to have the threads just say hello. Okay, so it's going to say, it's going to print out its own thread ID, and then it's going to say how many total threads there are. Okay, and so all of the threads in the parallel region are going to run this code. Okay, so yeah, so suppose you have, let's say 4 threads, right? Then you would be getting 4 of these messages. Okay. However, the messages can come out in some arbitrary order, right? because the threads are executing at different speeds and they're not synchronized with each other. Okay, so you could get maybe hello from thread 3 first, and then maybe thread 0, and then 1, and then 2. Okay, so the order is actually arbitrary. Okay, so next, let's see how threads can share some work. Okay, so so oftentimes you don't want threads to all do all of the work in the parallel region, right? You want them to you want to take the parallel region and divide that work into different chunks and give different chunks to different threads. Okay, so so that's work sharing. And one way you can do work, so one example of work sharing would be, suppose you have a big for loop in your parallel region. Okay, then you probably don't want all the threads to do all the iterations of the for loop, right? Let's say you have 100 iterations and you have 5 threads. Okay, you don't want all 5 threads to each do 100 iterations, right? Maybe you want each thread to do 20 iterations. Okay, so the way you can take this for loop and you can break up the for loop among your different threads is that once you're in a parallel region, okay, you can write this pragma OMP for. And now this is going to take this for loop and then break it up among all the threads that you created. Okay, so different threads will do different iterations of this. Okay, so so how do you know which threads are going to do which iterations? Well, this is controlled by this thing called a schedule clause. Okay, so I'll show you more details about this later. Now, this pragma OMP4, okay, so this doesn't start a team of threads, okay? So you have to use this pragma OMP4 within a parallel region after you've already created a bunch of parallel threads. Okay, this just tells OpenMP how to break up the work. It doesn't start any threads. Okay, it's the outside enclosing pragma OMP parallel. That's the directive that actually starts the threads. Okay, something else is that when you have this parallel for loop, right? So you have multiple threads and they're each doing some iterations of this for loop. So now there's actually an implicit barrier at the end of this for loop. Okay, so let's say that you have 100 iterations. Okay, so you could, and let's say you have 5 threads. Okay, so some of the threads might finish all the iterations that they're responsible for. They might finish that very quickly. Okay, but then after they finish, they're just going to wait at the end of this for loop. Okay, so they're basically going to wait over here. Okay, because there's an implicit barrier over here. Okay, and the thread is going to wait until all of the other threads doing the other iterations have also finished their iterations. Okay, so then after all 100 iterations have been finished, right, then the threads can go on to whatever's after this for loop. Okay, so this barrier is there automatically. You don't even have to specify the barrier. And but if you don't want there to be a barrier, right? If you want to say that, whichever thread finishes its iterations first, it can just go on to do whatever comes afterwards, right? Then you can put a no wait clause. Okay, so that removes the barrier. Okay, so now I'm going to talk about these schedule clauses. So the schedule clause is basically how you control which threads do which iterations of the for loop, right? So there are different types of schedules. So so the first schedule is the static schedule. Okay, so the static schedule has this optional chunk parameter. Now, if you don't use the chunk parameter, right? If you just say if you get rid of this, so you just say schedule static like that. Okay, then what's going to happen is basically it's going to take, let's say you have a bunch of iterations like this. Okay, so these are like a bunch of iterations, let's say like 1 to 100. Okay, right. Then if you have, let's say 4 threads, it's just going to break these 100 iterations evenly among your threads. Okay, so each thread gets 25 iterations like this. Okay, so thread 1 gets iterations 1 to 25, right? Thread 2 gets 26 to 50, right? And then 51 to 75, and then so on. Okay, If it's not, if you can't exactly break it evenly, if it's like 101 iterations or something, right, then one of these threads will get an extra iteration. Okay, but basically it's going to break it as evenly as possible if you just have schedule static like that without the chunk. Okay. Now, if you have the chunk parameter, it's going to do something somewhat different. It's going to do it somewhat differently. So the chunk is going to say that it's going to give a chunk number of iterations to each thread. Okay, and then it's going to do that in a round robin order. So, for example, what's going to happen is suppose the chunk here is 10. Okay, and suppose again you have 4 threads. Okay, so then thread 1, right, is going to get iterations 1 to 10. Okay, so that's thread 1. Right, and then thread 2 is going to get the next chunk of 10 iterations. So 11 to 20 is going to thread 2, right? Thread 3 is going to get the next chunk, 21 to 30, right? Thread 4 is going to get the next chunk, which is 31 to 40, right? And then since we're going round robin, we're gonna go back to thread 1. Okay, so then thread 1 is going to get 41 to 50. Okay, and then this is thread 1. Okay, and then thread 2 will get the next 10 iterations, 51 to 60, right? So I'm not drawing this right, but so then you keep going in the order of the threads 1, 2, 3, 4, 1, 2, 3, 4, right? And then for each thread, you give it the next 10 iterations, okay, if your chunk is 10. Okay, so but again, if you don't have a chunk, then you're not going to go through these threads multiple times. You just go through them once, and then each one of them gets, let's say, a quarter of the iterations. Okay, so there's also this dynamic schedule, so which also has an optional chunk parameter. So so each time a thread. Okay, so then here, for the static schedule, you assign all of the iterations at the beginning, right? So as soon as you start the for loop, you know exactly which threads are assigned which iterations. Okay, so that's why it's called static, right? Because it's assigned at the very beginning. For the dynamic schedule, you first assign one. So if you don't have this chunk parameter, then by default, you're just going to assign one iteration per thread. Okay, so then if you have 4 threads, right, thread 1 gets iteration 1, thread 2 gets iteration 2, right, thread 3 gets iteration 3, thread 4 gets iteration 4. Okay, and then after that, you're just going to let the threads run, and then one of them is going to finish its iteration, right? So so let's actually write this. Okay, thread 4, right? So initially it 1, 2, 3, 4. Okay, and then let's say that thread 2 finishes first. Okay, so at that point, it's going to get a new, it's going to get the next iteration. Okay, which is number 5. Okay, it's only going to get one iteration if you don't have the chunk over here, right? If you just write it like this, then you give one iteration at a time to the threads. Okay, and then let's say thread 3 finishes its third iteration, it'll get number 6. Okay. But then let's say that somehow thread 2 is very, very fast. Okay, so before, so thread 1 is currently processing iteration 1, thread 4 is doing 4, right? But before either T1 or T4 can finish, let's say thread 2 has already finished the 5th iteration. Okay, then it's going to get the next iteration, 8 or 7 rather. Okay, and then maybe T1 finishes, and then it's going to get the next iteration, which is 8. Okay, so just so for the dynamic schedule, you assign the iterations to the threads, but whoever finishes their assigned iterations first, he's going to grab more iterations. Okay, and the number of iterations he grabs is given by this chunk parameter. So by default, he's going to grab one new iteration. Okay, but if you set chunk to be like 10, then he's going to grab 10 iterations. Okay. So so there's some overhead to doing this, right? Because you have to now keep track of which threads are finished with their iterations, and then you have to assign them new iterations. Okay, but the benefit of doing this dynamic schedule is that suppose the iterations have different sizes. Okay, so like some of the iterations, let's say somehow are very cheap to do. Okay, and some of them are more expensive. Okay, so actually towards the end, we'll see an example where you have a for loop, but some of the iterations of the for loop are a lot more expensive than the others. Okay, so in that case, then for example, if T1 got a very expensive iteration, right? So let's sort of mark that with a circle. Okay, so if this is very expensive, then T1 might need to spend a lot of time on this iteration. Okay, but then maybe T2 got a very cheap iteration, right? So it can finish its iteration very quickly, and then it'll get the next one, right? And then the next one, and then the next one. Okay, right? So basically, for the dynamic schedule, whoever finishes first, because they had less work to do, they're going to grab more work. Okay, so this achieves better load balancing, right? Because if you don't use a dynamic schedule, if you use something like a static schedule, right? Then maybe you're going to assign thread 1, let's say 25 iterations. Okay, but maybe those 25 iterations are all very expensive. So then thread 1 is going to have to run for a long, long time. Okay, maybe thread 2 got another 25 iterations, but those are somehow very cheap. So then it's going to run very quickly. Okay, and then after thread 2 finishes, it's just going to stop. It's not going to do anything anymore. Okay, so now you're wasting a lot of cycles that thread 2 could be doing something useful. Right. So when you have imbalanced iterations, some iterations take more time than others, then you might want to use a dynamic schedule. Okay, there's you do pay some overhead for doing that, right? So if all the iterations have the same size, you don't want to use a dynamic schedule because you want to avoid that overhead. But if the iterations are really imbalanced, okay, then the dynamic schedule can improve load balancing and get you better performance. Okay, now there's this guided schedule. This is kind of like dynamic scheduling, except for you don't always grab the same number of iterations each time. Okay, so for a dynamic schedule, you always grab, by default, you just grab one iteration, but you could take like, if your chunk is 10, you'll take 10 iterations each time. Now for guided, you can actually take different numbers of iterations each time you grab something. So in the beginning, you take a lot of iterations. Okay, and then as you keep grabbing more and more iterations, right, each time the number of iterations you grab decreases. Okay, so this still helps you to do load balancing, but now there's less overhead to doing the schedule because now you don't need to grab chunks as many times, right? Because initially you grab a really large chunk, right? And then you keep grabbing smaller chunks, so you don't have to grab as many times as you would with a dynamic schedule. And then you can check the type of schedule that you're currently using using this variable OpenMP schedule. Okay, so let's see an example of this. Okay. So here, what happens is in a OpenMP program, the main thing that you parallelize, okay, like the most frequent thing that you parallelize are these for loops, because usually that's where most of the work in a program is being done in for loops, right? So if you want to improve the performance, you want to parallelize these for loops. Okay, so because you frequently need to parallelize for loops, then you can actually combine the parallel directive with the parallel for directive. Okay, so remember that previously we said in order to use a parallel for, right, you first of all have to go into a parallel region, right? To do that, you need to call pragma OMP parallel. Okay, once you're inside the region, you again need to call pragma OMP for. Okay, but to make it more convenient, you can actually combine the parallel region with the parallel for. So if you write this, the pragma OMP parallel for. Okay, this is both going to take you into a parallel region with multiple threads, and it's going to let you do a for loop in that parallel region. Okay, so this is just it's sort of syntactically like a convenience. Okay, it just combines both operations together. Okay, so this statement is gonna again, it's gonna create a bunch of parallel threads, and it's gonna split the for loop between those threads. And here we're using a static schedule, meaning that each thread is going to get the same number of iterations. Okay, and this is reasonable because you can see that all of these iterations have basically the same cost. Okay, so so by giving the same number of iterations to each thread, we actually achieve good load balancing. Okay, now there are several restrictions to how you use the parallel fors. First of all, the number of iterations, like this n over here, okay? So this is not allowed to change. So like you can't just modify n within your for loop, okay? And also the loop increment, right? So here we're incrementing I by 1 each time. This also needs to be fixed, okay? And then furthermore, within the loop, you can't just exit the loop prematurely, okay? You can't call a break or something in there. Okay, so basically the reason for all of these, for making these restrictions, is so that we know how many iterations are going to be executed in total. Okay, because for example, these schedule clauses, right? They need to know how many iterations you're executing in order to do the load balancing and the iteration assignment. Okay, so now I'm just gonna, so there are several different ways that you can write the parallel for, so I'm just gonna summarize them all over here, okay? So first of all, you can just do a sequential for loop, okay? So here you don't have any parallelism, right? So you just have a normal for loop like this, okay? You can also, first of all, create your parallel region using pragma OMP parallel, right? And then you can do the work sharing within that parallel region using pragma OMP4. Okay, so this is going to share the, it's going to split the iterations of the for loop between the threads, but you can also split them manually. Okay, so like if you have, so here you're just looking at how many iterations you're doing, right? You're doing n iterations, and then you have, let's say n threads, that's how many threads you have, right? So then you can manually, let's say you want to give the same number of iterations to each thread. Okay, then you can manually compute which iterations each thread should have. Okay, and then you can just, and then if you write this, right, then what's going to happen is when you go into this parallel region here, you create a bunch of threads. Let's say you create 4 threads for simplicity. Okay, so each of those threads is going to compute its own start and end indices. Okay. And then each thread is going to do this for loop over here, but different threads will have different start and end indices, and so that means that different threads will be doing different parts of this parallel for loop, of this for loop. Okay, so that's the manual way to do a parallel for loop, and you don't want to use this. You definitely don't want to do this manually. Okay, so here is where you combine the pragma OMP parallel with the pragma OMP4. Okay, you can combine them together into one statement. And then finally, this is not what you want to do. If you do something like this, then what's going to happen is here you create a bunch of threads. Let's say 4 threads, right? And then here this for loop is iterating over from 0 up to n. Okay, and now when you have 4 threads, all 4 threads are going to do all of the iterations from 0 to n. Okay, so you're doing basically 4 times as much work, right? You're duplicating the work 4 times. Okay, that's not what you want to do. Okay, you want to have each thread do 1/4 of the iterations, right? So yeah, so these 3 methods. Okay, this one, right? Or this one, this is actually kind of the preferred one, right? Or you can use that, or if for some reason you want to do this manually, you could in principle use this also, right? But you don't want to use this one. Okay, so there are other types of work sharing that you can do, right? So so you can divide a for loop, but there are other types of work that you can try to do in parallel. One of them is the sections. Okay, so yeah, so sections. If we look at this code over here, what's happening is so again we need to be in a parallel region. So we need to first call pragma OMP parallel, right? This starts a bunch of threads. Right. Now, within this parallel region, if you start a sections, right, a sections construct, right, with pragma OMP sections, then here you can define multiple chunks of work, right? So each section is basically a chunk of work, okay? And then now the threads that you started in your parallel region will be assigned to different chunks of work, right? So each thread can be assigned to any number of chunks of work, okay? So maybe some thread doesn't get any chunk of work, okay? And some thread might get many of these different sections, okay? But each section here represents some work to do, right? And then you've started some number of threads over here, and they're going to be mapped somehow to these different sections. Now, in this sections work sharing construct, there's also an implicit barrier at the end. Okay, so there's so if some thread finishes all its sections first, it's going to wait at the end of this sections construct. Okay, it's going to wait until all of the threads have finished all the sections, right? And then after that, all the threads will go on to the stuff after sections. Okay, if you don't want that barrier, again, you can use the no wait. Okay, now sometimes you're in a parallel section, but you don't want all the threads to do an operation. You just want one thread to do an operation. Okay, right? For example, if you're writing a file, okay, maybe you don't need all the threads to write the file multiple times. You just want one thread to do it. Okay, so to do that, you can use this single construct. Okay, so just write pragma OMP single, and then whatever stuff is in here, that's only going to be done by one thread. Okay, and that's not necessarily the master thread. Right. Okay, and yeah, and so even though this is being done by one thread, there's still a barrier that's implicit here, unless you use no wait. Okay, so that means that even though only one thread is executing here, the other threads are waiting at the end of this single statement over here. Okay, now for the single construct, I don't think you can control which thread is actually doing the stuff. Okay, but if for some reason you need the master thread to do that stuff, right, then you can call this master construct. So this is again going to be done just by a single thread, namely the master thread, and all of the so there's no implicit barrier. Okay, so then the master thread will do this stuff, but the other threads will go on to the subsequent stuff without waiting for the master to finish. Okay, so now we're going to talk about the OpenMP. We can share memory. So now let's see how we can actually share memory. Okay, so there are various commands for sharing the memory. Okay, so first of all, we can have both shared variables and private variables. Okay, so the shared variables can be read and assigned by any thread. But also threads can have private variables which only they can read and modify. So most variables are shared by default. Okay, so for example, global variables or static variables are shared by default, right? And also threads that the master thread, variables that the master thread declares are shared by default. Okay, but there are also variables that are that are private by default. Okay, so for example, if you have a parallel 4, right, then there's an index variable. Okay, now those index variables are private by default because if you have multiple threads and they're all doing this parallel 4, right, then of course you don't want them to use the same index because the different threads are doing different iterations of this parallel 4. Okay, so therefore each thread needs to have its own index into the for loop. Okay, also if you have stack variables, okay, so if these parallel threads call functions, right, then that's going to create stack variables. So those are also going to be private by default. Okay, so whichever thread calls a function, and if that function creates a bunch of stack variables, then those stack variables are private to the calling thread. Okay, and also automatic variables in the functions which you call in a parallel region, are also private by default. Okay, so now you can also control which whether variables are shared or private. Okay, so the way you can you can do that is using these shared or private constructs. Okay, so you write shared, and then you give a list of variables, and then those will become shared between the threads. Okay, if you write private with the variables, they become private. Okay, and then you can also make the shared variables by default shared or private. Okay, so so here's an example of controlling the sharing of variables. So suppose you have this variable x, right? Initially it's 5, and then we start a parallel region. But here before we start the region, you say that x is private. Okay, so this means that in this parallel region you have multiple threads. But now each of them will have its own copy of x. Okay, so so here each thread is going to get its thread ID and then set x to be the thread ID. Okay, and then but this is its own private copy of x. Okay, so that means that every thread will have a different value of x. Okay, and then it's going to print out that value over here. Okay, and then at the end of this parallel section, right, then x goes back to being shared. Okay, so x was shared initially, right, because it's a global variable here, right, and then it became private once you enter the parallel section, right, but then after you exit the parallel region, it becomes shared again. Okay, so then here, right, you're going to say that the shared x is equal to 5 again. Okay, yeah, so yeah, so this is summarized over here. Okay, now you have ways of setting the initial value of a variable. Okay, so you can use this thing called first private. Okay, so first private means that if you have like a shared variable, right, but then when you go into a parallel region, it becomes private, then what is the initial value of that private variable? So if you use first private, then the initial value of that variable is whatever value it had in the outside region before you enter the parallel region. Okay, and then also when you exit the parallel region, you might want to set you might want to take a variable which is private in the parallel region, and then you want that value to be adopted by the shared version of the variable outside the parallel region. Okay, and you can do that using last private. Okay, so as an example of this, right, so suppose you have a shared variable temp here, which is initially equal to 2. Okay, now you start a parallel region and you say first private temp. Okay, and you also say last private temp. Okay, so then what this is going to do is all right, and then within this parallel region, you're doing a let's see, a for loop here, right? Okay, so then here every thread has its own private copy of temp. Okay, but because you called this first private here, right, and because temp was equal to 2 outside of the parallel region, then then the initial value for this temp is going to be 2. Okay, so then here you're going to increment this 2, right, and then sorry, you're going to increment temp starting from 2. So then you're going to end up with some value of temp, which is more than 2. Okay, and then here when you call last private, this is saying that whatever value of temp you ended up with, right, this becomes the new value of temp after you exit this parallel region. Okay, so then here when we print the value of temp, we're definitely going to print something larger than 2. Okay, because temp here was initialized to 2, it got incremented some number of times, and then after you exit the parallel region, right, whatever the final value for temp, right, that becomes the new shared variable, shared value for temp. Okay, now there are these things called reduction variables. So this is important. So sometimes when you have multiple threads, right, you want them to access a common piece of data, So for example, you might have a like a counter. Okay, so you have a bunch of threads, and they each check, let's say, a data stream to see how many times something occurs. Okay, each time they see it occurs, they want to increment the counter, right? So now this counter needs to be shared between the threads, and so we saw that if you just have a normal shared variable and you have a bunch of threads modifying this variable concurrently, then you can have these race conditions where the variable ends up with incorrect values, right? And we saw that one way to prevent this was to whenever you want to access the variable, you include the variable in a critical section, right? You wrap it up in a critical section. Okay. However, yeah, so maybe here we have an example. Okay, so suppose you have a so this example down here, right? So suppose you have a parallel 4 where what we're trying to do is we have this array A, okay, and you want to sum up all of the values in this array, okay, into a variable x. Now, one way to do this is, well, we're going to start a parallel section here, and then, so this is a parallel 4, right? So then different threads will be assigned different iterations of this. So they'll be assigned different parts of A, right? And then they'll be reading this value of A and adding it to x, adding it into x, okay? But because this x is being shared by different threads, we need to make sure that the different threads don't sort of collide with each other. And so one way to do this is using this critical section to put a critical section around the axis to x. Okay. Now this will make sure that x does get the correct value, end up with the correct value, right? Which is equal to the sum of all of the array values. Okay. So this code is correct, but it's going to perform very poorly, because all of the threads keep calling this critical section. Okay, so this is a very expensive operation to call to try to take a lock in order to enter the critical section. Okay, so this code is going to perform very poorly. Okay, probably much more poorly than if you just did this entire for loop sequentially. Okay, so here we're trying to get some extra speed by parallelizing, but because you make so many calls to the critical section, you're probably going to hurt your performance by a lot. Okay. So instead, what we can do is we can use this parallel 4 reduction. Okay, so here we have a parallel 4, and we say that certain variables are reduction variables. And also, you have to specify how you're doing the reduction. So here we're saying that we want to add things into the value of x. Okay, sorry. Here you're saying that. Well, okay, so let me go through this first. Okay, so what's going to happen over here is when you have this reduction thing, this is going to make multiple copies of x. Each thread is going to end up with one copy of x. Okay, so if you have, let's say, 4 threads, you're actually going to create 4 copies of x, and each thread will have its own copy of x. Okay, own private copy of x. And so now when the thread goes to execute this parallel 4, right, the thread is assigned some iterations of this overall for loop, right? And it's going to add all of the values from the array into its own private copy of x. Okay, so now there's no collision between the different threads for accessing x, because each of them has a private copy. Okay, so unlike here, where all of the threads share the same copy, and so therefore you need to protect this copy with a critical section. So here, even though we're calling this variable x for all the different threads, it's actually a different variable for each thread. Okay, so therefore the thread can just add these values of a into its copy, and there won't be any race condition with the other threads. Okay, so at the end of this process, after a thread has gone through all of its iterations, right? So it was assigned some of the iterations of the for loop, and after it's done with all those iterations, it'll have its value of x will be the sum of the parts of a that it was assigned. Okay, so then each of the threads is going to end up with part of this overall sum of a. And now this reduction plus means that you want to take these private copies of x and then add them all together. And then when you add these all together, right, you get the sum for all of the elements of A. right? Because these elements of A were divided among the threads in some way, or partitioned among the threads, right? Every array element went to one of the threads, right? And then each of the threads took all the parts of A it was assigned and added them together into its private copy of X. Okay, and then finally, because we have because this X is a reduction variable, right? We're going to take all of those private copies of X and add them together, and that gets us the overall sum of X. And now this piece of code is also correct because it adds up all the values of X of A, right? And it's going to be much more efficient than this other piece of code over here, because here we don't need to use anything about critical sections, right? These are just regular additions, right? Unprotected by anything, so these are going to go very fast. Okay. All right, so next, so we just saw that we needed to, one way to protect variables. So here, this is not a good approach, but sometimes you do need to use critical sections. Okay, here you can get away with using a reduction variable, and that's much more efficient. But sometimes you do need to use critical sections, right? And the way you can use them is just with the pragma OMP critical. Okay, and then you can write, and then whatever piece of code goes after this critical, that is only going to be done by one thread at a time. Okay, so now you can also give, so you can also give a name to this critical section to identify it. Okay, if you don't give a name, then they default to having the same name. Now, in addition to critical sections, you can also have locks. Okay, in OpenMP. So the way you access these locks is through these various functions. Okay, you can initialize the lock, set the lock, unset the lock, test it, and then destroy the lock. Okay, so then here, the argument to the lock is a memory location. Okay. Now, what is the difference between a critical section and a lock? The difference is that a critical section is saying that a piece of code can only be accessed by one thread at a time. Okay, whereas a lock, here the argument to the lock is a memory location. Okay, so the lock is protecting the data to make sure that only one thread is modifying the data at a time. Okay, the critical section is protecting a section of code. So, so to give an example of how these are different, suppose you have a function which inserts into a hash table. Okay, so if you use a critical section around this hash function, then that means that only one thread can call the hash function at a time. So that means only one thread can insert into the hash table at a time. Okay, but maybe this isn't what you want, because if you have let's say a hash table like this, right? If the different threads are inserting into different locations, right? So if you have a thread, thread 1 is inserting here and thread 2 is inserting here, right? There's no problem having both of these run in parallel, right? So, but if you use a critical section, then either T1 can insert or T2, but you cannot run these in parallel. Okay. Now, what you do want to protect with this hash table is that you don't want T1 and T2 to write to the same location at a time. Okay. So what you can do is you can put a lock around these memory locations. Okay, so that will prevent different threads from writing to the same location at the same time, but it does allow different threads to write to different locations. Okay, because different locations, right? Each location has a different lock. So, so after T1 locks this location, it doesn't prevent T2 from locking this location. Okay, so so OpenMP also has barriers. Right, so we've talked about barriers. That's basically where you have, if you put the barrier, if you write this pragma OMP barrier somewhere in your code, that means that, so this has to occur in a parallel section, okay? But if you write this in a parallel section, that means that all of the threads are going to wait to get to that line of code before any of them proceed past that line of code, okay? Okay, so we have some additional synchronization constructs. So, for example, here we have these atomic constructs. Okay, so let's see. Yeah, so then so when you write this pragma OMP atomic, right, then only one thread can execute this statement at a time. Okay, so these atomic operations are just simple. They're limited to being simple operations, like maybe increment or max or test and set or something. Okay, yeah, but however, so when you do one of these atomic operations, so let's say you're doing atomic increment, okay, then when multiple threads call these atomic increments, you can be sure that each of the increments will be done by itself, will be done mutually exclusively. Okay, so if you do, let's say 10 increments, you're guaranteed that the value increases by 10, right? Whereas if you just do it without any protection around the increment, then you don't know how much the value is going to increase by. Okay, so basically the atomic operations are like a critical section. Okay, they protect this piece of code over here. However, they're limited because you're only allowed to do these few operations like increment or max or a few other operations. Okay, so they're bad because they're limited, but they're very good because these operations will be done in hardware. So this is going to be very fast. Okay, so if you put the increment inside of a critical section, right, then it's going to take you a long time to do that increment. But if you do an atomic increment, then because it's done in hardware, it's actually very, very fast. Okay, so the last type of, so one other type of synchronization construct is this flush flush command. Okay, so here, if you do pragma OMP flush, right, what's going to happen is you give a list of variables over here, and these variables will be now written from the buffer of a processor into the cache or memory. And once that happens, then all of the other processors will see the latest value of these variables. Okay, so the flush is basically a way for you to make sure that other threads see the same value for the variable that you have. Okay, so so the reason this is needed is because when one thread, so let's say you have a thread operating on this core. Okay, so when it's modifying variables, these variables might be stored in these buffers for efficiency purposes. Okay, these buffers can be accessed very quickly. Okay, but when they're in these buffers, then the variables are not visible. The values of the variables are not visible to any other threads in a different core. Okay, so you might have modified these values here and nobody knows about your modifications. Okay, and that's bad because now it seems like now there are multiple copies of this variable. Right, there should only be one copy of a variable in a shared memory setting. But if the variable is stored in the buffer, then different processors could have different values for this variable. Okay, so in order to make sure that all the threads have the same value for the variable, you need to take this variable and flush it out from these buffers into either the cache or the memory. Okay, if you flush it out into memory, then the other threads can definitely see the value, right? And if you flush it out to cache, then because you usually have a cache coherency protocol running, then the cache coherency protocol is going to basically send the latest value to all of the other processors that are accessing this variable. Okay. Okay. So next we have these things called ordered statements. Okay. So the ordered statements basically they so you use these ordered statements inside of parallel fors. Okay, so what's going to happen is the ordered statement lets you do part of this parallel for in parallel, but once you get to the ordered part of the parallel for, then these will be done exactly in the order of the iterations. Okay, so for example, in this example over here, right, if you have this parallel for, then this stuff up here, okay, if we have multiple threads, then this stuff up here will be done by multiple threads in parallel. However, for the ordered part over here, right, these will always be done in the order of the iterations. Like so, the iterations are going from 0 to n, right? And so so the increments will always increments and decrements to s and t will be always done in the order 0, 1, 2, and so on. Okay, so basically, the reason we use this is so that here we can still get some parallelism, right? Because here, since we're not inside the ordered statement, we can do multiple things in parallel. Okay, but here you might have some things that for some reason you have to do these in the loop order. Okay, so this ordered statement lets you combine parallelism with something that you have to do in loop order. Okay, so when you use these ordered statements, you typically want to use a static schedule with a small chunk size. Okay, and the reason is that, so here we can consider two examples. Okay, so suppose you have a for loop with, let's say, 9 iterations and 3 threads. Okay, so now if you do, if you use a static schedule, but you don't specify the chunk size, then every thread will get, basically, you have 3 threads, so they're going to get 3 iterations, 1/3 of the iterations, right? And so thread 0 will get the first 3 iterations, and then thread 1 the next 3, and then so on. Okay, so now let's see what happens when you go execute this for loop, and suppose it's got an ordered statement in there. Okay, then since we need to execute this ordered statement exactly in the loop order, then what's going to happen is that there's a little part of this for loop, right? So these this part over here, right? So this corresponds to this part, which can be done in parallel across all the different threads. Okay. However, the ordered part, right? That's what these circles are. These have to be done in order, right? And because thread 0 has the first 3 iterations, you have to let thread 0 do the first 3 iterations. Okay, and then only after thread 0 has finished its 3rd iteration can you have thread 1 do its 3 iterations, right? And then only after thread 1 finishes can you have thread 2 do something. Okay, so basically we've sequential. So if you use a static schedule, right, then you basically have sequentialized this entire computation, right? Because you see that over here, right, both thread 2 and thread 3, threads 1 and 2 are not doing anything. Right, they're waiting for thread 0 to finish with its ordered iterations. Okay. However, if you use a different schedule, if you use, for example, static with a small chunk size, let's say of 1, right, then what's going to happen is, remember, for the static schedule with a chunk size of 1, we're going to assign 1 iteration at a time to the threads in round robin order. Okay, so this means that thread 0 gets assigned the first iteration, right? And then you assign 1 iteration to thread 1 and then 1 iteration to thread 2, right? And then you go round robin, so you give 3 to 0, right? Iteration 4 to 2, and then so on. Okay, so we assign the iterations this way, right? Now what happens is, now if you execute this for statement with the ordered statement, right? This for loop with the ordered statement, you see that, well, again, we have this part, which corresponds to this part, which can be done in parallel, right? You see that this is being done in parallel across the 3 threads, right? And then you have to wait for the first iteration to finish, right? So that's what's happening over here. But as soon as the first iteration finishes, okay, so here you have the 2 threads. They're idling because they're waiting for the first iteration to finish, right? But as soon as that iteration finishes, thread 1 can now do its iteration. For this ordered part, right? And so and then after that, thread 2 can do its 3rd iteration, right? And then in the meantime, right, the threads can go back to doing this parallel stuff. Okay, so here we have more parallel stuff that's being done, right? Yeah, and then after you do the parallel stuff, you again get to the ordered part. Right? So again, you have to wait for iteration 3 to finish before you do 4, before you do 5. But here you see that there's a lot less waiting, right? You see that there's a lot more parallelism when you do the when you do this static schedule with small chunk size compared to just the normal static schedule. Okay, so all right, so next we have a few functions that we can call to find out some conditions about the runtime environment. So for example, these functions can tell us the number of threads, or set the number of threads. You can also do that, right? You can control how many threads you have, and you can also have a thread find out its thread ID. Okay, you can find out how many processors you have, because it might be like a multi-core, multi-processor system. And then you can find out whether you're currently in an active region or not. And then you can even dynamically adjust the number of threads in a parallel region. Okay, so that basically describes the how we use OpenMP. So now I want to give an example of actually doing a problem using OpenMP. Okay, of actually computing something using OpenMP. So the problem we're going to look at is how to compute the Mandelbrot set. Okay, so basically the Mandelbrot set is so we're going to look at all of the complex numbers. Okay, so imagine that you draw the complex. Actually, maybe I should draw it differently. So imagine that you draw the complex plane. Okay, so here you have all of the real numbers, right? And then here you have the imaginary numbers. Okay, so let me just write this as real, right? And then here you have the imaginary numbers. Okay, so for example, this value here might be something like 1 plus I. Okay. Now, what this Mandelbrot set is it's a subset of this complex plane. Okay, so it consists of some of these points. So some of these points are in the Mandelbrot set, and the other ones are not. Okay, so then the way it's defined is that you're going to take a complex value like this, and you're going to keep iterating that value through a function like this. Okay, so you take this function and then you keep iterating this function, and the initial value of the function is going to be some number from your complex plane. Okay, so what this function is that let's see, it's so initially you're going to set z. You're going to set you're going to set z0 to be some complex number. Okay, so something like a plus I times b. Okay, and then you're going to square this z, right? So you're going to square this z0, and then you're going to add some constant c over here. Okay, so the c is some other complex number. Okay, so that gets you a new number which you're going to call z1. Okay, and then you're going to take z1 and you're going to square it again, and you're going to add c to it. Okay, and that gets you z2, right? And then you do it again, you get z3, right? So you do z2 squared plus c, and then you get z3, and then you just keep doing this. Okay. Now, what you're looking for is eventually you're looking at the sort of the limiting value of these z's. Okay, so imagine that you do this iteration like an infinite number of times. Okay, now one thing that can happen is if you do this an infinite number of times, then maybe the z's keep getting larger and larger. So the z values go off to infinity. Okay, if they go off to infinity, then you say the value is not in the Mandelbrot set. Okay, however, for certain initial values of z0, these values might actually might stay finite. Okay, so for example, if your c here, so let's set a value for c. Okay, so let's say it's like 0 over here. Okay, and let's say that your initial value here was also let's say it's 1. Okay, it's just equal to 1 plus 0 times I. So then if you keep squaring this, right, this does not grow to infinity. It just stays at 1. Okay, so if after you keep iterating these values, if the limiting value of z is finite, then you say that this initial value of z is in the Mandelbrot set. Okay, so that's how we define this Mandelbrot set. So I'll show you some pictures to make this more clear. Okay, but that's the definition. And okay, so let's go with the picture first. Okay, yeah. So here we have this beautiful picture. So this is the Mandelbrot set. Okay, so what this is saying is basically all of the points, all of these black points. Okay, these are points of the complex plane such that if you iterate this function, right, z squared plus c, even if you do this an infinite number of times, okay, these values do not diverge to infinity. Okay. However, for these other colored values over here, right, these values, if you iterate them many times, right, they do diverge to infinity. Okay, so this is so if you look at this, for example, if you pick a point over here, okay, this is a very large point, right? Let's say it's something like 2 plus 2 times I. Okay, well, if you take 2 plus 2 times I and you keep squaring it and then adding some value to that, right? Then then this value is going to get larger and larger, and it's going to blow up and go off to infinity. Okay, so that's why this point is not in the Mandelbrot set. Okay, whereas this point here, right? This might be the 0 point. Okay, so if you take 0 and you keep squaring it, right? It's not going to blow up and go off to infinity. And so this is in the Mandelbrot set. Okay, so what's really interesting about this figure is that the set of points which are in the Mandelbrot set versus not in the set, right? They have this incredibly intricate pattern, right? Like, for example, here, these points, they are in the set, but if you just move a little bit, then they're outside the set now. Okay, so there's a huge amount of detail to these points. So you can't really see this on this figure, but these little arms that are shooting off of the circles, right? So these arms have very, very detailed structures, okay? And the sort of incredible thing is that even if you were to zoom in on one of these arms, okay, they would still have more detail. So in fact, you can keep zooming in over and over onto any region of the Mandelbrot set, and you would never see that this region becomes like smooth eventually, right? Meaning that, so the region would always show more and more detail. Okay, so let me illustrate that with this movie over here. Okay, so this movie is initially we're very far away from the Mandelbrot set, and what we're going to do as I play this movie is we're going to zoom in onto the Mandelbrot set. Okay, so here you see the scale of the zooming. Okay, so you see that we're zooming in onto the Mandelbrot set, and we're zooming in on these little arms over here, and you see that we're going to see more and more detail up here. Okay, so you see that even as you zoom in, you see more of these little circle things. Okay, in fact, this Mandelbrot set is a fractal, meaning that you see the same pattern basically appear over and over, but it's not exactly the same pattern. Okay, it looks similar, but it's somewhat different. Okay, so here as you zoom in, right, it's incredible. I mean, you have this spiral, and there's just more and more detail in this spiral. Okay, no matter how you zoom in, you never get to a region which is like either completely black or completely light. Okay, right? So here we've zoomed in. You can see this is already we've zoomed in by a factor of 10 to the 10th. Okay, so 10 billion times, and yet we still see more patterns in this. Okay, so I think how long is this video? I think that there are a few more interesting features which all right, so let's let this run a bit longer, because I think at some point a very cool thing starts to happen, if I remember correctly. All right, so let's wait for a bit more of this. Okay, right, so you see all these patterns, and you kind of see that these patterns are similar to the patterns that we've seen before at higher resolutions, right? But they're not exactly the same. Okay, so things do kind of repeat, and yet they're different. Okay, so now here's the incredible thing that happens. Okay, so remember the initial shape that we started with, which was this circle thing, that this sort of heart-shaped thing. Okay, so now we've zoomed in by a factor of 10 to the 20th. Okay, and somehow miraculously, right, this shape has reappeared. Okay, and if you were to zoom in by another 10 to the 20th, then well, I don't know about this, but I think the shape can reappear again. Okay. So anyways, I find this to be very cool, and so this is the Mandelbrot set. And what's even more amazing about this is that all of it is defined by this incredibly simple expression over here. Okay, so you just start with a complex value, right? You keep iterating that complex value over and over, and if it diverges, it's in the Mandelbrot set, and if it if it diverges, it's outside the Mandelbrot set. If it does not diverge, it's in the set. Okay. Now, you notice that there are these colors here. Okay. So strictly speaking, a value is either in the set or not in the set, right? So we should actually have a black and white figure. Okay. So the colors are actually indicating how quickly a value diverges. Okay, so somehow these colors are set to correspond to how quickly a value diverges. Okay, so that makes the picture look a bit nicer. Right? Okay, so now it's actually very easy to construct the Mandelbrot set. Okay, we can write a simple function to compute the Mandelbrot set. So what we're doing over here is that given a particular pixel C, right, we're just going to iterate this this starting value multiple times. Okay, and we're going to see if it diverges or not. Okay, and the number of times we're going to iterate is we're just going to iterate this 256 times. Okay, and the criteria we're saying is that if after 256 iterations, right, if this if this complex value is sufficiently large, okay, then we're going to say that it's going to diverge. But if it's small, right, if the length of this complex value is less than 4, right, then we're going to say that we're going to assume that the value does not diverge. Okay. Now we could be wrong because so we're iterating this 256 times, right? It could be that after 256 iterations, the value has not diverged yet. But if you iterate this a few more times, then it does diverge. Okay, so this is possible. Okay, but for simplicity, we're just we're fixing the number of iterations, and then we're checking the size of this value at the end of this. And if the size is less than 4 here, then we're going to assume that it does not diverge. Okay, and now these computations, all they're doing is they're just computing this. They're doing this calculation over here. Okay, so this calculation, remember z, these are complex values. So so we're going to split this z into the real and the complex part, right? And now if you want to square z, right, the real part becomes a squared minus b squared, right? So the current value of z, let's say, is a plus bi. Okay, so if you want to square this, the real part is a squared minus b squared. The complex part is 2 times ab, right? And then we need to add this to c. And then it's known that if the magnitude of this z, okay, so this is a complex number in the complex plane. So if the magnitude, which is the distance away from the origin, if this is ever larger than 2, then this value definitely will diverge. Okay, if it's less than 2, then it's not guaranteed that it will converge. But if after 256 iterations, it still is the magnitude is less than 2, then we assume it does converge, and then we say that it belongs to the Mandelbrot set. Okay, so that's the computation for computing whether one value c converges or diverges. And when you compute the Mandelbrot set, you need to know this information for all the values in the complex plane, right? So then what we do is we just divide this plane into a bunch of pixels, and for each pixel, we run this calculation over here, right? And so all of the pixels are completely, all the computations are completely independent from each other, right? So therefore, we can run all of them in parallel, okay? Now, the only question is, if we have a bunch of parallel threads, right, how many pixels do we assign to each thread? So one simple way is using a static assignment, right? So a static assignment would be, so we're going to iterate through all of these pixels in a double for loop, right? So this is iterating through all of the rows, right? And the other one is iterating through all the columns. Okay. Now we can parallelize this. We're going to parallelize just the outer for loop. Okay. So we're going to parallelize all the rows of the plane, and we can use just a basic static schedule. Now, if this happens, if we use a basic static schedule, this is actually not efficient. Okay. And the reason is that if you look at the Mandelbrot set, okay, so what's happening is if you use a static schedule, then maybe thread 1 is responsible for, let's say, these these rows over here, okay, and thread 2 might have these rows, right? Thread 3 these rows, let's say 4 and then 5, okay. Oops. Okay. Now the thing is that thread 1, because it's taking care of these rows, right? These values here are very large. Okay. So if you run this this calculation here, then after just a few iterations, you're going to see that these lengths are going to exceed 4, and so you can already stop the for loop, right? The while loop. Okay, so therefore each of these pixels over here, right, though you just run the while loop for a few iterations, so they're very quick. Okay, so all of these computations just take a little bit of time to do. Okay, now over here, if you look at T3, okay, so it's responsible for these this part of the plane. Okay, and for example, for these values, right, so these values don't diverge. So even after you iterate them 256 times, they still don't diverge. Okay, so that means that T3 has to run all of these values, has to iterate all of them for 256 times. Whereas T1 over here can iterate all of these values just for a few times. Okay, so that means that T1 is going to run much faster than T3. Okay, if you assign T1 these rows and T3 these rows, then T1 is going to finish a lot faster than T3, and so you have a lot of load imbalance. Okay, so so that's not efficient because we have load imbalance, and so in order to make things more efficient, we're gonna not use a static, not use a default static schedule. We can, for example, use a static schedule with a chunk of 1. Okay, so if you use a static schedule with a chunk of 1, then what's going to happen is you're going to say that, so this top row here, let's say that gets assigned to thread 1, right? And then this gets assigned to thread 2, 3, 4, right? And let's say you have 4 threads, okay? So then you're going to go round robin, and so you're going to assign these in this order, okay? So then in this way, you see that thread 1, right? It's assigned some of these easy rows, right? But it's also assigned some of these hard rows, okay? These hard rows where you have to run for a long time, okay? So basically the amount of work for each thread, you can see that each thread is assigned some of the easy rows and some of the hard rows, okay? So the work is much more balanced if you use the cyclic assignment, okay? Or you can use the dynamic assignment, okay? Or you can use a guided assignment. Okay, but all of these will achieve much better load balancing than just using the default static assignment. Okay, so so the final thing I want to say is now there are a few other ways to do shared memory programming. So there are these things called PGAS languages, which people have been looking at for the last few years. So they're not very popular right now. So not many people are using them. But there is a hope that somehow they have better performance properties than OpenMP. So they're still being researched, and perhaps in the future we'll start using them. So so therefore, to finish up, I just want to mention a few of these languages. Okay, so so PGAS stands for Partition Global Address Space. Okay, so basically the idea is that we're going to treat so in shared memory programming, all the processes or all the threads can access this entire chunk of memory, okay? But that doesn't mean that the memory is all stored at one location and all threads have uniform access to all chunks of memory, right? I mean, you know, a thread might be able to access some pieces of the memory faster than other pieces, right? Even though it can access everything, some accesses are faster than others, okay? So then the idea for PGAS is to take this entire chunk of memory and then and then sort of bind each thread with the memory that it can access most quickly. Okay, so there's some subset of the memory space that each thread can access most quickly, and so we want to take the entire address space and partition it and sort of give each thread the part of the memory that it has the fastest access to. Okay, the thread is still allowed to access the other parts of memory, but it will usually try to do its operations in the chunk of the memory that it's been assigned, where it can operate the fastest. Okay, so yeah, so that's the basic idea for the basic motivation for PGAS languages. So there's no language that people have agreed to use no single language that people have agreed to use for PGAS. Because it's still sort of at the research stage. So there are several different PGAS languages like Unified Parallel C or Co-Array Fortran, Global Arrays, and so on. Okay, so in some sense, these languages are actually quite similar to OpenMP because they're also based on they're mostly based on parallelizing loops. Okay, but the difference is that in OpenMP, the threads don't really have any idea, don't really differentiate between different parts of the memory space, right? They don't differentiate between the parts they can access quickly versus the slow parts. Okay, whereas in PGAS, right, this is the thing that you add. Okay, threads treat different parts of the memory space differently. Okay, so there are also a few other asynchronous PGAS languages like X10 and Chapel. And so here, for example, a parent thread can spawn and sync and join with child threads. Okay, yeah. So again, they're not widely being used right now, but there is hope for them in the future. Okay, so we have this global address space that all the threads can access, and then it's divided into partitions, and each thread has what's called an affinity to a partition. Okay, so for example, if we look at the let's see. Okay, so let's actually go back all the way to the beginning of this lecture, right? So physically, what happens is you might have a CPU, right? It might have some memory which is local to it, okay? And then this memory is local to the second CPU, and so on, okay? So the affinity of the memory to the CPU is just whatever memory is local to a CPU. That's the memory that has affinity to that CPU. Okay, so now let's go back to this. Right. Okay. Right. Yeah. So the memory is partitioned so that you sort of you have this affinity between the processors and the memory. Yeah. And so this PGAS languages, they basically capture data locality, right? Because each thread is aware of how far away the data is from it. Okay. Whether it's in its local memory, in which case it's sort of fast and nearby, or whether it's in some other processor's memory, in which case it's slower. Okay, so it supports all the basic functions that you need, like private or shared data, and then dynamic memory allocation and all that. Okay, so they're pretty complete languages, but the performance currently is not that good. Okay, so the whole point of PGAS languages was to get better performance, but currently you still need to sort of tweak these languages or tune your code a lot before you can get really good performance. Okay, oftentimes in parallel computing you need to process arrays. Okay, so in PGAS you can also partition the arrays across the different threads. Okay, so that way you can make sure that the part of the array assigned to a thread, right, that thread has very quick access to that array because that array is stored in the thread's local memory. Okay, so so as an example of this, suppose we have 4 threads. Okay. Then in one of these PGAS languages, the Unified Parallel C, right, we have this way of distributing an array. So if you allocate the array like this, right, so then what's happening here is that we have a 4x4 array, right? So threads is 4 here, and then we're going to split this into based on chunks of 3. Okay, so what's happening is that we have 4 threads. So initially we allocate 3 of these array values to the first thread, right? And then we allocate the next 3 to the next thread, right? So we're going, A00, 01, 02, and then when you get to 03, right, you actually give that to the next thread, right? So we're going row by row over here, right? And then so the next value after A03 is going to be A10 because we have 4 values per row. Right, so these 3 values go onto thread 1, right, and then after that, the next value after A11 is going to be A12, and so the next 3 values go onto thread 2, the next 3 values go onto thread 3, right, and then the final, the next after A23 we have A30, right, and then the next 3 values go to thread 0, and the final value goes to thread 1. Okay, so this is like one way that you can partition a matrix or an array among multiple threads. right? And then you would be choosing, you as a programmer get to choose this parameter over here based on the size of the array and based on how many threads you have. So you would try to choose a way to partition the array so that each thread is assigned a part of the array that is stored in its local memory so that it has fast access to that part. Okay, so UPC, you can also parallelize for loops, right? Just like you can in OpenMP. So here you initialize a for loop. You have a test. This is how to update the loop variable, right? And then you have this affinity. So this affinity is going to control which threads execute which iterations of the loop. Okay. So then here you have an example of a for loop. Yeah. So you can basically do all the things that you have in OpenMP. So you have barrier synchronization and locks, and then you also have memory fences, and then there are even relaxed memory models. Okay, so and then finally there are another few methods that you can do shared memory programming. So I mentioned when we talked about MPI that the newer versions of MPI, MPI 2 and 3, right, they actually support these one-sided communication. Okay, so this means that instead of one process sending a value and another process receiving, right, you can actually just directly write a value to some other process, okay, without having to pass these messages. So that's kind of like doing shared memory programming. Okay, and something else is that so usually we think of MPI for distributed memory programming and OpenMP for shared memory, right? But there's no reason that they're exclusive to each other, because, and in fact, in many parallel computers, right, you have these nodes of processors which all do share a common block of memory. Okay, so within each node, it makes sense to run OpenMP. Okay, however, you could also connect many of these nodes over a network. Okay, and so for communication between different nodes, since different nodes cannot directly access each other's memory, it makes sense to use MPI for communication between nodes. Okay, so basically you can use a combination of MPI and OpenMP. Okay, and then newer versions of MPI even support threads, so that even within MPI itself, you can do shared memory programming. Okay, so this is all we have to say. All I have to say about OpenMP. See you all next time.